I've done an example in a previous video where we approximated the area caught between a non-negative function, the x-axis, over a closed interval by just using our numbers and our formulas from geometry. In this one, I'm going to still approximate that area using formulas from the geometry, but I'm also going to use more notation involved in that process that will eventually lead us to being able to apply our calculus techniques to find the exact area of that plane region. So here, when we want to approximate the area of a plane region caught between a non-negative function, that means its graph is above the x-axis over the interval, possibly touching the x-axis, but not going below it. Y equal f of x, the x-axis over the closed interval from a to b, using n equal width subintervals. Now certainly this can be done if you don't have your equally width subintervals. I'm just choosing to have equally width subintervals for this example. Now what we are going to do is kind of get a picture idea of it and then go through the steps of what we would need to do in order to find an approximate value for this area. So I've graphed a non-negative function over the closed interval from a to b. So your interval from a to b is on your x-axis. And then I drew a vertical line at the start of the interval a and a vertical line at the end of the interval b. Now what we want to do is take that interval and break it up into n equally width subintervals. And when we are asked to approximate this area, they're going to give us a value of n they want us to work with in that approximation, or give us some information to determine what our n should be. Then, once we break it up into the sub-rectangles, we want to apply our properties and formulas from geometry in order to get the approximation. Now, one of the earliest formulas for area in geometry that you get is the area of a rectangle. And remember, the area of a rectangle, we can either say that it's length times width, or we can say that it's base times height, in either of those specific types of vocabulary. Well, then we want to draw rectangles that somehow get an approximate fill for this region. Now what we're going to do that is we'll find our subintervals, and then we'll take vertical lines up to the function on whichever endpoint we're deciding to use, and then make that the top of our rectangle. So our width of our rectangle is going to be this distance on the x-axis, and our height of our rectangle is going to be what we get for our function value. And then we're going to apply that formula for the area of a rectangle. And we'll do it for several rectangles and then add them up. This is a step-by-step way of just kind of keeping your thoughts together in terms of what you need to do. So delta x, the increment in x that will take you from the start of the interval and work your way across, we find delta x by taking the end of the interval, the right endpoint of the overall interval, minus the beginning of the interval. So we're going to go b minus a and divide that by n, how many equal subintervals that you want. When we're first approximating the area, we are going to have a specific numerical value for n. When we get to the point that we're actually finding out what the exact area is using our formulas and using our limiting process, then our n will be the variable n instead of being a specific number. And that'll be our limiting variable when we get to that part. But for these problems, for the examples that I'm going to give you in this video, n will be a specified number in the example. Now find your subintervals. So I want to find the x values that hit right on the intervals as we go. So as I've drawn that one, I have 1, 2, 3, 4, 5 for my n. I'm going to write it out here in general and then actually use specific numbers when I get to an example. So find my subintervals. Well, my very beginning of my interval is A for the first one. And then that interval starts at A, and then it goes to this next spot over, which that value will be A plus delta x. And to kind of clean it up a little bit, they actually use subscripts on x values to be where you hit across your horizontal axis, your x-axis. So they say your start of your overall interval is x sub 0, and then x sub 1 is A plus delta x. It's the first x you encounter in that walking across on the interval. So this will be A and then A plus delta x. We'll write it that way first, and we'll come back with the other notation. Now when I pick up, I'm going to have A plus delta x. So from A to A plus delta x is this first subinterval. Now I'm going to pick up the start of the next subinterval as A plus delta x, and then I'm going to add another delta x to that. So the next one over is A plus 2 delta x. And that's called my x sub 2. Then the next one over is A plus 3 delta x. And that will be our x sub 3. And you continue on that pattern. So the next one will pick up with the A plus 2 delta x and go and finish at A plus 3 delta x. And then you just continue that pattern. So then if I look at this as my subscripted x's, my first interval is x sub 0 comma x sub 1, and then x sub 1 comma x sub 2, and then x sub 2 comma x sub 3, and then you keep going until you hit right before that last one, or hit that last interval. That last interval will start at A plus n minus 1 times delta x, and then it'll end on B. And when I look at that interval, you have your x sub n minus 1 and then end up at x sub n. So your x sub n, when you do the subscripted value that matches what your n value was, that should land on the end of your interval. And if it doesn't, then you need to go back and look at your arithmetic and see what happened. Now, last video that I did approximating the area actually just did numbers there instead of our notation, but I need to bridge the gap between just using numbers to getting more comfortable with the notation so that you're ready to go on to that next step of finding the exact area. Okay, now we want to find the heights of the rectangles. Now, they could ask us to find the heights any given x value within each subinterval. And so I have to pay attention to what they're asking me, whether it's right endpoints or left endpoints or midpoints, any sort of thing like that. So for the right endpoints, I look at the first subinterval, left hand, right hand. In this first subinterval, my right endpoint is the one my right finger is pointing to. So when I look at that, that is the A plus delta x. That's my x sub 1. So I'm going to bring my vertical line up to the curve. That's how tall it is. And then do a horizontal line segment across so that I make my rectangle. So that's visually showing you finding the height from the right endpoint. And so for the right endpoint, my first rectangle's height is the output of the function when I plug the right endpoint through. So that's going to be f of x sub 1. But remember, x sub 1 is a plus delta x. And then the height of the next one is go to this next subinterval, find your right endpoint, take it to the curve, and then horizontally across. So that's your x sub 2. So that's f of x sub 2. So this is the height of my first subinterval. This is the height of my second subinterval. So if I keep going across with that, I'll do this until I get to the last subinterval. And so that would be my f of x sub n for the height of that last one. Now what about if I were trying to find the heights, if it was a different question and they asked me to use the left endpoints. So for the left endpoints, I would go to my first subinterval. This is my left hand. So I'm going to run this x sub 0 through the function to get the height. And then I have to do a horizontal line across to the right to hit the subinterval and down. So this height is the output at the left endpoint, and for my first subinterval, the output at the left endpoint I will get by running the left x value through the function. So this is my f of x sub 0 for the first rectangle height using the left endpoint. And then for the second subinterval, I'm going to run the x sub 1 through the function and get its height. And then for the third subinterval, I'm going to run the x sub 2 through the function and get the height. So my first subinterval, my x that I went through is x sub 0, and I ran it through the function to get the height. So for my very last rectangle subinterval, left endpoint, I'm going to run x sub n minus 1 through the function to get the height. Now, as you get these, you're going to have as many heights as you have rectangles. So if they said to make 4 subintervals to do the area approximation with 4 rectangles, then you should only have 4 heights. And that can kind of be a double check for you to count up and make sure you don't have too many. Now, how do we find the approximate area? Here's another place where our notation comes in that we want to get comfortable with. Remember, we'll kind of write it out here and then go to that. So if we're talking about the right endpoints, the area approximation, well, I want to find area of each of these rectangles. So here's my first subinterval. My right endpoint took me to the curve and back over, so it's this one. And the formula for finding the area of the rectangle, we're going to take the height, the length times the width. So my length is what I get out when I ran that x value through the function. I got the function value out. So that's going to give me my height, f of x sub 1, times how wide that rectangle is. And it's a delta x wide. And then plus, go to your second rectangle. Its height is f of x sub 2 when I'm using the right sub endpoints, and then the width is delta x. And then plus f of x sub 3 times delta x, and then plus all the way out to f of x sub n times delta x. So that's it written out. How does this get represented by that? Well, remember, summation is to add, and I am adding up all of these areas of these subrectangles. So here's my summation to add, that's representing that plus. And then I want to go I just being my index of summation. So sometimes people use a K for their index of summation if they don't use an I. I'm using an I, so that's what I'm subscripting each of the things for. So I equal 1 to n, whatever your specific n is now for these area approximations. Later on, again, it'll stay the variable n. And then my inputs through my function. So my f of c sub I, that's your height of your subrectangle, and then the delta x sub I is your width. So there's your height times your width. That's the area of your subrectangle. Now, why did I call this c and I call those x's? Well, the c just gives you a little bit more of a generalization of c can be any x value in that interval. It could be the left endpoint, it could be the right endpoint, it could be the midpoint, it can be any value in that subinterval. So the actual c that you will use when you get to a problem will be determined by whether they asked you to do the left endpoint or the right endpoint or the midpoint of the subintervals. So this is just more general, broader van of types of problems. So you're going to plug that x value through your function to get your height, and then this delta x sub I. These I'll just say delta x's because I picked to do equally width subintervals across. So for my example, I really don't need a delta sub I on that because they're all going to be the exact same value through it. But if you did pick different widths of your subintervals as you go, then you would need the width that goes with that subinterval. So if one width was a half, and then another width was a third, and then another width was 5/8, etc., that would need to change by which one you're working as you go across. So again, that's more general. Okay, now if we were going to do the left endpoints, then for the left endpoints, your area is approximately, well, look at your first subinterval, look at your left hand, and the very first one put through was the x sub 0 through the function to get the height for the left endpoints. So this one's going to be f of x sub 0 times delta x for my first subrectangle's area, plus f of x sub 1 times delta x for the second one, and then you're going to go out to f of x sub n minus 1 times delta x for the last rectangle. Because remember, left endpoint, it would be this one run through, which is right before you get one step before you get to the end. And then run that through the function, that gives you the height. So that would be that area. And then with these, then adding them up, whichever one that we do, the left or the right endpoints, then when you add up those areas, you get approximate value to the area of the overall thing.